Assalamualaikum warahmatullahi wabarakatuh and greetings. We are from Group 22. We'll present about our article and case study, which is evaluating the efficiency of renewable energy technologies through thermodynamic analysis. My name is Muhammad Dini Khalis bin Rostam, and the first part is introduction and problem statement. So the introduction is renewable energy technologies such as solar thermal, biomass, and geothermal are increasingly used due to rising energy demand, environmental concerns, and limited fossil fuel resources. Although these systems are cleaner and more sustainable, their efficiency and performance still face challenges. Thermodynamic analysis helps evaluate how effectively renewable energy systems convert energy into useful output. By applying concepts like energy efficiency, exergy, and entropy, we can identify losses and improve system design and overall efficiency. So, for the problem statement, despite the increasing use of renewable energy technologies, many systems still operate below their optimal efficiency due to thermodynamic losses and irreversibility. Traditional energy efficiency analysis does not fully explain performance degradation because it ignores exergy destruction and entropy generation. Factors such as heat losses, temperature differences, combustion inefficiencies, and poor heat transfer reduce the effectiveness of solar thermal, biomass, and geothermal systems. Therefore, a comprehensive thermodynamic and exergy-based analysis is needed to identify these inefficiencies and improve system performance. Next. So next is about the fundamental of thermodynamics. So the first law of thermodynamics, which is law of energy conservation. The first law of thermodynamics states that energy cannot be created or destroyed, only converted from one form to another. In renewable energy systems, this law is used to calculate energy efficiency by comparing input energy with useful output energy. Some energy is always lost to the surroundings during the conversion process. Next is second law of thermodynamics, which is entropy and irreversibility. The second law of thermodynamics explains that all real processes generate entropy. Because of this, energy conversion systems can never be 100% efficient. Higher losses and temperature differences increase entropy and reduce system performance. And lastly, heat transfer fundamentals. Heat is transferred through conduction, convection, and radiation. Heat losses during transfer reduce system efficiency. Proper heat transfer design improves energy conversion effectiveness. That's all from me. I will pass to Naufal Bukhari. Thank you.
Thank you, Nicholas. Now, my name is Muhammad Naufal Buhari bin Rasman. I will explain the actual engine that makes renewable energy possible, the thermoelectric, specifically the Rankine cycle. So, please look at the diagram on slide 3. Most thermal renewable technologies, such as solar thermal, geothermal, and ocean thermal energy conversion, rely on this four-stage loop to turn heat into electricity. Step 1 is the pump. We start with the pump, increase its pressure, preparing it for the heat phase. Step 2 is the boiler or heat exchanger. This is where the renewable source come in. Whether it's concentrate sunlight or heat from the Earth's core, it boils our fluid into high pressure vapor. Step 3 is the turbine. This is the most critical part. The high pressure vapor expands through the turbine blades, spinning a generator to produce the electricity we use in our homes. Step 4 is the condenser. Finally, we use cold water, sometimes from deep ocean in OTEC system to cool the vapor back into a liquid so the cycle can start all over again. The article highlight that choosing the right working fluid, like a water specialized organic fluid, is what determines how much power we can actually squeeze out from this cycle. So next slide is energy losses and exergy destruction. Why are we this system is not 100% efficient? In thermodynamic, we look at the losses in a two-way. That is energy and exergy. Energy loss is simple. It's heat escaping through pipes. But exergy destruction is more important. It represents the permanent loss of energy quality due to entropy. Where these losses happen primarily in three places. First is heat transfer. When there is a huge temperature gap between the sun and our fluid, we lost potential work. Second is friction. The physical movement of fluid through valve and turbine blades creates resistance. 3. Throttling. Sudden pressure drops that degrade the energy usefulness. As you can see in the Senkai diagram on the slide, the useful energy arrow gets thinner at every stage. By using the thermodynamic mentioned in our article, engineer can pinpoint exactly which component is failing and improve its design to minimize this waste. So I pass to my next friend, Adam Mukris. Thank you.
Thank you, Nofal Bukhari. Good day, everyone. Today, I will briefly explain the thermodynamic analysis of two major renewable energy sources, which is solar energy and wind energy. And first, I will start with solar energy. Solar energy originates from nuclear reactions in the sun and reaches the earth in the form of solar radiation. From a thermodynamic perspective, solar energy is considered a thermal energy source. The solar radiation is absorbed by solar collectors and converted into heat. This heat is transferred to a working fluid, which operates in the thermodynamic cycle, such as the Rankine or organic Rankine cycle, to produce mechanical work and eventually electrical energy. In terms of efficiency, solar energy systems are evaluated using both energy efficiency and exergy efficiency. Although the energy input from the sun is large, the exergy efficiency is relatively low. This is mainly due to large temperature differences between the solar source and the surrounding environment, which cause high irreversibility and entropy generation during heat transfer. As a result, practical solar energy systems operate far below their theoretical efficiency limit. And next, I will move to wind energy. Wind energy is derived from the kinetic energy of moving air, which is created by uneven heating of the Earth's surface by the sun. Unlike solar thermal system, wind energy is a mechanical energy source, not heat-based. Wind turbines convert the kinetic energy of air directly into rotational mechanical energy. Experiences losses due to aerodynamic effect, mechanical friction, and electrical inefficiencies. In conclusion, both solar and wind energy are important renewable sources. Solar energy is abundant but limited by thermodynamic irreversibilities, while wind energy offers higher energy efficiency but constraints by aerodynamic limits. Understanding this thermodynamic characteristic is essential for improving renewable energy system performance. Thank you. And next, I will pass to my friend Muhammad Irfan Takif.
Okay, thank you, Adam. Okay, in this presentation, I will briefly explain how thermodynamic analysis is used to evaluate the efficiency of renewable energy system, focusing on geothermal energy, hydropower, biomass, and biofuels. Both energy and SLG perspectives are used to understand the system performance and losses. First, geothermal energy. This energy converts heat from the earth into electricity using the Rankine or organic Rankine cycle. Energy efficiency is defined as the ratio of electrical output to thermal energy extracted and is highly dependent on the temperature difference between the heat source and the environment. However, SSG analysis shows that major losses occur in heat exchangers and turbine due to irreversibility. The organic Rankine cycle helps reduce these losses for low temperature sources. Okay, next, hydropower energy. Hydropower converts gravitational potential energy of water directly into electricity. Its performance depends on the water flow rate and heat difference or heat. Hydropower is highly efficient, typically 90, 95 to 85 to 95% because it involves minimal heat losses. SLG destruction is very low, mainly due to mechanical friction, making hydropower one of the most efficient renewable energy systems. Moving to biomass energy. This energy is a chemical energy in organic materials. It's converted into power through combustion or gasification. Energy efficiencies are generally 20 to 35%. As G energy reveal large losses in combustion and heat transfer process due to high entropy generation. Finally, biofuels such as ethanol, biodiesel, and biogas. These are produced from biomass using biochemical or thermochemical process. Thermodynamic efficiency depends on the fuel heating value and conversion method. LSG analysis indicate irreversibility during fermentation and chemical processing, which reduce overall efficiency. Despite lower energy density, biofuel have reduced net carbon emission when produced sustainably. Thank you. Next, I will pass to Muhammad Shauki Fitri.
Thank you, Irfan Takib. So, for my part, I will conclude all the presentation for today. So, the conclusion for this presentation is from this article, we can see that renewable energy technologies play important role in dealing with global energy challenge. As energy demand continue to grow, renewable energy provide a cleaner and more sustainable option compared to fossil fuels. The article also point out that different renewable energy technologies perform differently. Each system has its own level of efficiency and effectiveness, so they cannot be evaluated in the same way. Because of this, proper evaluation methods are important. They help us compare these technologies fairly and identify where improvement can be made. The study also emphasized that continued improvement in both design and operation is necessary to improve the performance of renewable energy system Overall, the article showed that renewable energy technologies have strong potential to deliver reliable and cleaner energy in the future. So next, I will talk about sustainability consideration. When it comes to sustainability, renewable energy systems have to reduce our reliance on fossil fuels, which are limited and harmful to environment. Improving system efficiency allow us to make better use of natural resources such as sunlight, wind, and water. Using renewable energy also result in lower emissions, which helps reduce environmental impact and support efforts to address climate change. Sustainable energy development is important to ensure long-term energy security, especially as global energy demands continue to increase. So lastly, the article highlight that careful planning and continuous evaluation are necessary to ensure that renewable energy technology remain effective and sustainable in the long run. So next, for the overall conclusions, we can relate it with thermodynamics principle, which is essential for evaluating renewable energy system. Energy efficiency is limited by entropy generation and irreversibilities. As energy analysis better identifies usually energy loss than energy analyzed alone. Reducing thermodynamic loss improve system performance and efficiency. And lastly, thermodynamics evaluation support sustainable and optimized renewable energy development. So that's all from us, which Group 22. Thank you and enjoy the video.